but I minimally want to get far enough so at least you see what some of the issues are about how the ideas of locality and gravity, how locality and gravity conflict, how it shows up in a big macroscopic way in the context of the information problem where we think we know the right answer. And if I have some time, I'll tell you at least some of the thoughts I've been having recently about how this impacts our understanding of de Sitter space. But, you know, those thoughts are pretty primitive anyway. So I think you should take the whole story up to that point as inspiration to think about this problem yourselves, because I think, as you'll see, there's really a puzzle, and I really suspect someone is going to come along and just tell us how to think about this whole problem the right way, and we'll all say, aha, and it'll just make a lot of sense. Okay, but let's, so we talked about entanglement. I want to now talk a little bit about locality first, again, without gravity. And remember, why do I care about talking about locality? It's because when we go back to this crazy picture of eternal inflation, okay, the reason we get into all these confusions is because we draw a huge spatial slice. It's infinitely big. This point and that point and that point are all space-like separated from each other by definition. So in terms of an underlying semi-classical quantum field theory, we would assume that the operators, any local operators at all those points commute. Therefore, there's some infinite dimensional Hilbert space. Okay? And there is this part and that part and that part, and so that's where we start getting into trouble. It's locality that tells us all the regions on the space-like slice are independent. And if they're all independent, then we have to start worrying about why we're in one and not the other, and so on. Okay? And how can this possibly be wrong? You know, curvatures are low compared to the Planck scale. Everything is low. How can it possibly not be true that this thing is independent of that thing is independent of that thing? Well, precisely analogous words were used in setting up and arriving at the black hole information paradoxes I will review for you. And so we know that there is something wrong with these words. Okay? We know that from the context of black holes. I want to try to characterize what's wrong with those words in a little more detail so we can figure out more concretely how to apply the lesson from the black hole case, where we think we know the right answer, to this case, where we don't yet know the right answer. Okay? But anyway, that's why I want to start off talking about the idea of locality. So this could actually be an entire lecture in itself, but for reasons of time, I'm going to be a little briefer about it. In quantum field theory, the most primitive way in which we talk about locality, even let's say in Minkowski space, is a statement that operators that are space-like separated from each other commute. Okay? And in a more general curved background, this would just be space-like separated. Okay? Now, this is something you can do when you have the luxury of an off-shell formulation of the whole theory, like we tend to have in local quantum field theory. We don't have an off-shell formulation of string theory. We don't, and actually by now we even know many more examples of interesting theories, which aren't gravitational even, like little string theory. Okay? Little string theory is a nice non-gravitational theory without a good off-shell formulation. So what I want to tell you is something a little less familiar, which is how do we understand locality when you don't have, more in terms of direct, actual observables. Okay? So one thing we'll review in a second, but you've all heard of, is that, you know, if you have asymptotically flat space, the only rigorous observable that we have is the S matrix. So how is locality encoded in the S matrix? And of course, this is something that all the S-matrix people from in the 60s thought at great length about. And I want to tell you what the answer is. And I want to motivate the answer. Well, so certainly what we can do is the following. We can start with local quantum field theories where we know what locality means. In local field theories, we can compute the S-matrix, and then we can see what property of the S-matrix in local field theories is reflecting this fact. Okay? And the words are the words you've all heard. It's the analytic properties of the S-matrix, the fact that the S-matrix in appropriate variables can be extended to an analytic function in the whole complex plane, except on the real axis, where at most it has poles or cuts. And there's an additional thing which is not as often remembered, which is also that the S-matrix has certain exponential boundedness properties. Okay? But I want to motivate both. It would take 2 lectures to go through all of that, but I want to do it in 5 minutes. And I can do it by 5 minutes by motivating it, roughly. You see, what we're doing is trying to find what is the mirror of this statement in position space, roughly speaking, in momentum space. Okay? So let's do in the S-matrix. Okay? So let's do a very simple example. Suppose we have a function of x, just a function of one variable, that vanishes sharply outside some interval. Okay? Exactly vanishes outside some interval. That's supposed to reflect that condition on the left. How is that fact encoded in the Fourier transform of that function? That fact is encoded in the Fourier transform by the fact, first of all, that this integral really only runs from L1 to L2. Okay? And this immediately tells us 2 things. One, it tells us that f twiddle of p is analytic in p. It's analytic because it's a sum of a bunch of analytic functions. And the only place non-analyticities normally come in is from the limits going from -infinity to infinity, which doesn't happen. 2, it's exponentially bounded. Okay? Again, it's a sum of a bunch of exponentials, so it's exponentially bounded in the entire complex plane. Okay? So if we take familiar examples, like if you take that to be f of x, you know that f twiddle of p is sine p over p. Okay? So sine p over p is exponentially bounded, and it's analytic everywhere. Okay? If we take f to look something like e to the minus magnitude of x. Okay? So this does not vanish sharply outside some interval. How does that show up in the Fourier transform? The Fourier transform is 1 over 1 plus p squared, non-analytic. It has a pole in the complex plane. Okay? And finally, if we take a Gaussian, e to the minus x squared, then this is e to the minus p squared. It's not exponentially bounded. Okay? So the functions of p that are it's not exponentially bounded in the complex plane, right? It goes like e to the minus x squared. So along the imaginary axis, it's blowing up more quickly than e to the x. So if someone hands you a function of p and says, you know, does this correspond to something that vanishes sharply outside an interval in x? The way to check is to see if it's analytic, if it can be extended to be analytic in the entire complex plane, and if it's exponentially bounded. Yes? Not analytic. Okay. Now, this statement translates into the analog of these statements for the S matrix. I will just tell you, and they're the same statement basically. But let's say we're talking about 2 to 2 scattering. So we're talking about an amplitude as a function of s and t. Then the statement is, 1, that the amplitude is analytic in st, except possibly on the real axis, where it has cuts. And 2, m at high energies is exponentially bounded. So this is interesting. It tells you, in particular, that the amplitude along the real axis which typically falls with energy, right? The amplitude along the real axis falls with energy should be greater than e to the minus root s, or e to the minus energy. If let's say I'm working at fixed angle, so I'm only interested in the dependence on energy. It should be bigger than something. The amplitude should be larger than e to the minus energy. And actually, when you do it a little more carefully, there's a log energy here. And this is something that, so root s log s, e to the minus energy, log energy. These logs show up all over the place in field theory, but anyway, it's not important. But you see, these statements are really the moral analogs of those simple statements there. Okay? And so these are the properties of the S matrix that reflect the underlying locality of quantum field theory, okay? Or of any local theory. But then we should actually invert it. Okay? Since the S matrix is the only rigorous observable that we have, this should be the definition of locality. Okay, of course, when we have an off-shell formulation, we know what locality means. But when we don't have one, the definition of locality is someone hands you an S matrix. A, you should find that it's analytically continuable, and B, you should find that it's exponentially bounded. Okay? If it is, then it has all the properties that I mean, it's the only sharp notion of locality. It's a sharp notion of locality. Okay. Now, I say this because in a moment we're going to turn on gravity. But actually, this dispels a myth that many, many people still have, which is that string theory is non-local. String theory is damn local. Of course, that shouldn't surprise you because string theory came out. Now, what I mean perturbative string amplitudes. Perturbative string amplitudes are damn local, and perturbative string theory is damn local. And it should not surprise you because it came out of the S matrix program. Okay? So it came out of precisely trying to satisfy all of these rules. And in particular, even though we don't have an off-shell formulation, we can compute perturbative string amplitudes. And perturbative string amplitudes satisfy these properties. In fact, it's very nice. Notice the fact that it's analytic is true of field theory and string theory. Field theories tend to not even come close to meeting this bound, right? Because in field theories, amplitudes fall like 1 over powers of energy. So amplitudes are way bigger than e to the minus energy at high energies. Okay? In perturbative string theory, naively, if you look at the Veneziano amplitude, it looks like the Veneziano amplitude at very high energies compared to the string scale violates this bound. Remember, the Veneziano amplitude goes like e to the minus s, e to the minus energy squared. And that's faster than e to the minus energy. However, it's also been known since the work of Gross, Mende, Oguri et al. That very high energy fixed angle scattering in string theory is not dominated by the Veneziano amplitude. It's dominated by a much larger genus surface with G comparable to the energy in string units. And the amplitude that you get from that dominant contribution is exactly e to the minus energy log energy. Okay? So it's very striking, in fact, that while field theory doesn't even come close to saturating this bound, string theory saturates this bound. It's as local, perturbative string amplitudes just go right up to meeting this bound, and so there's no evidence for lack of locality in perturbative string theory. Yes?
You said a couple times.
I'm clearly talking about closed strings, and I'm talking about in fact, attempts. Closed strings are important for everything that I'm talking about here, and people have tried. In fact, Gross and Erler and others have tried to talk about these things in string field theory, and of course, there's all of these arguments also assume things about. When we say quantum field theory satisfies these bounds, it assumes things like finite number of species, et cetera, things that are violated in string field theory anyway. Okay? But what I want to stress is that this is a completely invariant characterization of locality. It's purely in terms of observables. It's a property of the S matrix. It's a formalism independent statement, okay? And so if we know the answers, however you get them, we find that indeed the perturbative string amplitudes satisfy these constraints. Okay. All right, so that's what locality means, both in this in the off-shell, more familiar off-shell, and this more on-shell language. If I say it yet another way, you know, the S matrix is, in a sense, in asymptotically flat space, the S matrix gives us purely boundary information. Okay, and yet you believe that there is a bulk theory. So how is it possible that just with boundary information you can reconstruct the bulk theory? Well, it's possible because the boundary information has a very special property. It's analytically extendable. Okay, and that analytic extendability is what allows you to reconstruct everything that's going on in the interior. Okay, it doesn't have to be. I could give you an S matrix that's Lorentz invariant and unitary, for example, but which was not analytic. And that's possible, and it just does not correspond to a local theory, and you would not be able to reconstruct bulk physics unambiguously. Okay. Okay. So now let's see what happens when we turn on gravity. Okay. Well, let's see what happens to these various notions of locality. Notion one, that the operators commute outside the light cone. And here's the problem. What the hell does outside the light cone mean? The metric is a quantum variable. Okay? So what am I supposed to say? It's when this is 0, when the expectation value of g mu nu, delta x nu. This is a nonsensical statement. Okay? I can't have an operator statement hold only for certain states. So it's just physically because the light cone fluctuates, the metric fluctuates. There's no well-defined notion of a space-like. So this notion of locality is clearly gone, okay, at a formal level. Now, people also say, that another signal is that we don't have gauge invariant local observables. That if I talk about something like 5x, 5y, that this isn't diff invariant. Because under diffeomorphisms, the point x and y move around. Now, I want to talk about these arguments a little bit because neither the previous argument nor this one has seemed to have anything directly to do with G Newton. Okay? But what I want to tell you is that the notions of locality are screwed up because of dynamical gravity, actually because G is not equal to 0. Okay, so I want to just give you a characterization of, okay, maybe locality doesn't make sense, but what does that mean operationally? How much doesn't it make sense? How much, what kind of effects should we expect, and so on, okay? And this argument does not depend on G Newton at all, okay? In fact, this is a really silly argument, because you know that diffeomorphism invariance, like any gauge symmetry, is completely meaningless, okay? Gauge symmetries are redundancies of the description. They have no physical content at all. And it's very surprising to have something with no physical content tell you that local objects don't exist. Let me bring this point home a little more. Clearly by taking a limit of GR where I send G to 0, or I send M Planck to infinity. Okay? This is going to be a very useful limit for us to consider over and over again, just to disentangle what is trivial from what is deep. Okay? In this limit, there's no dynamical gravity, but the theory is just as diffeomorphism invariant as it was before, right? So So how is this theory diffeomorphism invariant? Well, it's very easy. It's in fact very easy to make any theory diffeomorphism invariant because diffeomorphisms are fake, like every gauge solution. But how does it work in this case? Well, in this case, it works that by setting in Planck to infinity, let's say I'm working in flat space with zero cosmological constant. Okay? If I set in Planck to infinity, it's impossible to make any curvature, right? I'm setting r to 0. So G mu nu must be diffeomorphic to flat space. Okay? Now, so I'm writing it in a way that's then manifestly diffeomorphic to flat space. So now let's take this theory. So it's just the usual theory we had before, but everywhere there's a metric G mu nu, replace it by this object. The y's are just 4 scalar fields. And they transform in a specific way under diffeomorphisms. Well, we know how they transform because we know how G transforms. But let's say I have some other scalar field, 5x. I know under diffeomorphisms, I replace 5x by phi of zeta of x. And the way that the y's transform under diffeomorphisms is that y goes to zeta inverse of y of x. Y mu of x goes to zeta inverse of y of x mu. Okay, that's how it. That's the way it inherits the diffeomorphism properties of the metric itself. So this is a theory with 4 scalar fields, y alpha. They transform under diffeomorphisms like this, and now you can make any theory diffeomorphism invariant like this that you want. Okay, everywhere you see the metric, replace it. So this is what we get in the limit as we send G to 0. And there are local operators. Of course, there must be, right? This is a theory without gravity. But in case, just so it's clear, I'm talking about a theory without any dynamical gravity now, which is just as diffeomorphism invariant. Okay? This is a trick you can do to any theory. You can always introduce a gauge symmetry. Okay? Gauge symmetries are a fake. You make a gauge transformation and you promote the gauge transformation parameters to fields, and ta-da, the theory is gauge invariant. Okay? It goes under many names. It's a Stuckelberg trick. It goes under many, many names. Now, there is, of course, a very natural way of fixing a gauge. So because there's gauge redundancy still here, there is a natural gauge where y is equal to x. Okay? You can think of the y's as just giving you a freedom to choose any set of coordinates that you want. Okay? So this is the gauge fixing. But even before gauge fixing, there's a perfectly nice diffeomorphism invariant 2-point function. That is diff invariant. Okay? That's because y of x is diff invariant. Y of x goes to zeta inverse of zeta inverse of. It's phi of y. I'm sorry. Phi of y. Phi of y of x goes to phi of zeta inverse of y of x, which is phi of y of x. Thank you. Okay. All right. So it's not diff invariant. Now I did this in the limit as I decouple gravity, but in fact, I don't have to take such extreme measures. You see, again, gauge symmetries are a redundancy. Gauge fix, that's what we do. Once you gauge fix, you're done. Every observable, everything that you want to talk about in the gauge fix theory, you're allowed to talk about. GR has a very nice, manifestly unitary gauge fixing. You know, there's analogs of the Coulomb gauge, okay, analogs of axial gauge. So you just fix the gauge. Fixing the gauge means picking a set of coordinates. Okay, you pick a set of coordinates and they're local observables. Everything is perfectly fine. Okay? In this language, even if I don't send G to 0, I can always write the metric. You see, the time and space coordinates, the clocks and rods are the y's here. Okay? And I can always write g mu nu as the gauge transformation of something. I can always write it as d mu y alpha, d nu y beta, of eta alpha beta plus h alpha beta, where the h satisfies the certain constraints, transverse traceless, whatever. Okay? And I have manifestly gauge invariant. I have manifestly gauge invariant local quantities, which are precisely the same as the quantities I would compute in the gauge fixed theory. Okay? That's not the problem. This shows you that there's no problem with talking about local observables in gravity to any order of perturbation theory. Okay? I can have a Hamiltonian formalism of gravity. I can compute anything I want. Of course, it's not renormalizable, but I include higher derivative operators, as usual in effective field theory. There's no problem in any order of perturbation theory. Okay? So these arguments are too quick. Also the first argument I told you that we can't define local observables because of the fluctuation of the metric. Equally too quick. Okay? I can take a theory with gravity, I can gauge fix, then the graviton is just another, spin 2 degree of freedom around the fluctuating background. It's just as local as anything else. Okay? So what does it mean? So is there a content then to the statement that there aren't local operators? There is content. But as I'll argue, it's because the notions of locality are not violated at any order of perturbation theory. It's e to the minus 1 over g effects. E to the minus 1 over g Newton effects that screw up notions of locality. And in fact, really what it is, as we'll see, is always e to the minus some area over g effects. It's e to the minus what we've learned to associate with entropy in gravity. Area is divided by g. Okay? So it's e to the minus s effects that screw up notions of locality. So let's see how that works. And furthermore, it should also be clear, they all have to do with strong gravity, in particular, things like black holes. Okay, so let's talk a little more pragmatically. Yes. I mean, that's something that isn't captured as small perturbations around a fixed background. That's what I mean. I don't mean hyperbole. Okay. So let's say you go to your experimentalist friend and you believe these arguments. You don't quite know, but you don't know exactly. Well, you tell them, hey, quantum gravity says there aren't any local observables. And they say, what are you talking about? I measure local observables all the time. So how do you answer them? Well, this is the answer. So let's say the experimentalist tries to set up an experiment to measure the two-point function, 5x, 5y. Okay? Now, what do you have to do? Well, first of all, it's quantum mechanics. So what we have to do is we have to have a big apparatus here, a big apparatus here around the points x and y, because of what we talked about yesterday. Okay? And secondly, you got to make many copies of this. Maybe you do the experiment over and over again here, or you believe in translational invariance and you move the experiment around in many places, and you have to do the experiment n times. Okay? But what do they actually do? They make a histogram. They say, here are all the allowed values of 5x, 5y. I do the experiment n times, and they have a whole bunch of bins for the different values of 5x, 5y, and they make a histogram. And the claim is that the histogram gets very, very narrow and sharply peaked around some answer. And as n goes to infinity, as they do the experiment n times, this goes like 1 over root n. As they do the experiment n times, this becomes arbitrarily sharp, and that's the answer. Okay? So, and before n is infinity, the experimentalist will tell you that, look, jerk-all, 5x, 5y is equal to my measurement plus or minus a statistical error, plus or minus a systematic error. And they're statistical errors because they do the experiment a finite number of times. And the systematic errors, well, you know, they have to measure very, very finely different values of 5x, 5y. Okay, so if they want to work so hard to measure many, many different possible values of that, great. But anyway, at any time they want to stop, they'll report the answer to you at this level. So they say, what do you mean this quantity doesn't exist? Well, you have to go back to them and say, all right, can you make a perfect experiment? Can you actually make an experiment that would reduce both your statistical and systematic errors to 0? And they would say, sure, I'll just do the experiment infinitely often. That makes a statistical error go to 0. And I'll just make these bin sizes as small as I want, and that'll make the systematic error go to 0. And that's where the problem begins. They cannot, for a variety of reasons, send the systematic error to 0. And it all has to do with the fact that their apparatus here has to become larger and larger and larger to send that systematic error to 0. But as this apparatus becomes larger and larger, it inevitably becomes heavier and heavier. Okay? And as it becomes heavier and heavier, you can no longer neglect its back reaction on the geometry. In fact, it'll eventually become so heavy that it would collapse this region into a black hole and remove the possibility of even doing the experiment. Okay? So this happens in a whole variety of ways, but let me tell you one of them. Okay? So it's a combination of things, not just the fact that just from yesterday, in order for any of these things to be perfectly sharp, we have to send n to infinity. Okay? So let's actually stop, first of all, and say, how big can the Hilbert space of these apparatuses even be? How many states can these apparatuses have, consistent with this picture of the space-time? And there's a limit. There's a limit to the total number of states of the apparatus. There's a limit to the total number of states of the apparatus, which is bounded by e to the power of the entropy of the black hole that would eat up the points x and y. Okay? So this is e to the x minus y, roughly speaking, to the d minus 2 over g. This is a very deep fact about gravity. Any way you think of building that apparatus up is going to make it heavier and heavier. And, well, something you know is that the object in a given region with the most number of degrees of freedom is a black hole. So there's no way that your apparatus, if it's not a black hole, is going to have that many degrees of freedom. Okay? This already tells us, just from yesterday, that we have a limit. That the total number of possible states in the Hilbert space of the apparatus is bounded by e to the s. So there's inevitably, in our decoherence formulas, in our measurement formulas, and all of that stuff, there's e to the minus s's floating around all over the place that we cannot send strictly to 0. Okay? Related to that, these are all the same thing. If I want to make these bins finer than e to the minus s, I have to have more than e to the s registers here to be able to record those different values of 5x. And I can't do that. Okay? So this is the key problem. This is the key point. It's because gravity does not allow you to separate the system from the apparatus arbitrarily sharply. And what's special about gravity? It's its universal attraction. It's the fact that it keeps building up, the fact that it can't be shielded. Okay? So this is the answer. The answer to your experimental friend is that this quantity that you're computing, I'm sorry, is just a crappy approximate quantity. It's not exactly sharply defined. There's no experiment that will give you an exact sharp answer for it. And the uncertainty in this two-point function is of order e to the minus s. So e to the minus x minus y to the d minus 2 over g. Okay? So this is compatible with everything we said before. This is never going to show up in any order of perturbation theory. This is why doing gravity in a fixed background, including all possible small fluctuations, is fine. Okay? But it's this thing to do with the fact that in a given region, we just cannot have more than e to the s degrees of freedom that limits the amount by which we can separate system and measuring apparatus gives an inevitable systematic uncertainty in any local quantity that we might want to measure. Okay. So this is one view. We can see this in a completely different way and get the same answer to give us confidence that this is the right answer by seeing how this breakdown of locality shows up in the S matrix. So let's say we're talking about 2 to 2 scattering. So something is happening here at fixed angle. I just told you that perturbative string theory doesn't violate locality. Okay? But when you go to very high energies, eventually even perturbative string theory breaks down. And that happens when what? When gravity starts becoming strong. That happens, roughly speaking, when the energy gets so big that the Schwarzschild radius of the would-be black hole with that mass gets comparable to the string length. Okay? You start making black holes. Now, at energies parametrically higher than that even, we don't exactly know the two-point function. So we don't exactly know the S matrix. But there's a very natural guess for what the S matrix should be in that limit. Okay? At least I know that it can't get smaller than the following. There's always some amplitude for these two guys to make a black hole and have the black hole not decay with Hawking radiation, but very rarely just decay back out in two particles. Okay? And that amplitude is around e to the minus the entropy of the black hole with energy E. Okay? This is e to the minus E, so the entropy of a black hole is always its mass times its radius. So this is e to the minus E times the radius of the black hole with energy E. And now the point is that it's GE over R to the D minus 3 is equal to 1. That's what defines a black hole. Okay? So R goes like some power of the energy. Now, this is a really small amplitude, and one has to be sure that there aren't effects that are bigger than this. Okay? But it's at least a plausible guess that this is what the 2 to 2 scattering amplitude looks like at very, very high energies, roughly. By the way, you get the same answer. This is a very nice exercise to do. You get the same answer if you ask the following question. Let's say you take a shell that's collapsing to form a black hole. Okay? Now, if you just look at the mechanics of that shell, of course, it's a relativistic mechanics. But even in the non-relativistic limit, it looks like, and generalizing the relativistic limit, it looks like a potential that looks something like that. Okay? There's some kind of runaway potential, and that's why you start the shell at big R and it just rolls to small r, to 0R. In fact, so it would look like that close to the horizon. You go from the R to the tortoise variables, and it actually looks like an exponential potential like this. But anyway, classically, then, if you send something off with asymptotically zero velocity, it just rolls, and you make a black hole. But quantum mechanically, if someone hands you a potential like this, and you have a little wave packet, well, there's always some amplitude for it to bounce. Okay? We don't normally talk about this when we talk about tunneling. We talk about things like that. This is another example of something like tunneling, where you have classically something would just go flying down a potential, but quantum mechanically it can bounce. You've broken translational invariance, so there's no symmetry reason that it shouldn't bounce. And it bounces. Okay? So you can actually do the computation in this case, and you can compute. It's a very simple application of the WKB approximation. You can compute what the scattering amplitude is, and you find that it's exactly e to the minus the entropy of the black hole. Okay? So these are a variety of ways of thinking about why the answer should be e to the minus the entropy of the black hole. Now notice that this is smaller than e to the minus e log e. Okay? So the last sharp vestige of locality that we could have had is finally gone when you have black hole production. Okay? That's another indication that has to do with strong gravity. And furthermore, if you take this result for the amplitude and you try to reconstruct a local object from this amplitude by Fourier transforming back into position space, you find that there's an ambiguity in that Fourier transform, precisely because things don't fall off fast enough in the complex plane. And the magnitude of that ambiguity is exactly that much. Okay? So I think this is a completely independent set of arguments that there is a fuzziness to our notions of locality, but that it's an e to the minus s effect. Okay? I should say, I mean, this is not, I don't think, universally agreed on. There are papers in the literature that claim that there are effects that are perturbative in G. Okay? And I just don't believe it, both because there's no signal for it in perturbation theory, and if it was true, the entire apparatus of effective field theory would be useless. Effective field theory is all about helping you compute things that are perturbative in 1 over the cutoff, and I just find it highly implausible that effective field theory is completely useless. Okay. Yes. Right. Well, so I gave you two views on the problem. One very concrete, physical. The other more formal. Okay. Yeah.
So it doesn't matter where I place it. Like, there's a background black hole geometry. Would it introduce some changes to it, or it doesn't matter where I place it?
So let me say this. So how do we get around this? What kind of observables can we have? Clearly, the sort of observables we can have are ones that allow us to separate the points off to infinity. Okay? Because when I can separate points off to infinity, I can make the apparatuses arbitrarily big, and I can reduce the systematic error to 0, finally. That's why observables in gravity are associated with boundaries. Okay? Because only when you have that can you make sharp, are there sharp observables. Okay. Now, so we went through all the song and dance, and you told your experimentalist friend that there are e to the minus s effects that mean that the things they're measuring aren't really sharp, exact observables, and they laugh at you because they say that the effect, forget it being perturbative in G, which is already incredibly tiny, it's e to the minus 1 over G, for heaven's sake, right? So these are minuscule effects, minuscule effects. Where should these effects become important? Only at the Planck scale, okay? So that's the naive idea, that quantum gravity, for example, here the fact that there's no locality, should only show up at the Planck scale. And that's what's actually wrong. Because there's a way for it to show up macroscopically if somehow you find competing e to the plus s's elsewhere that can amplify the size of this effect. Okay? So I have to, of course, this is very rough. I have to tell you in what sense it can amplify and so on. But just even very, very grossly, you should expect that it doesn't matter at all until you find a situation where somehow you're compensating for the e to the minus s size of the effect by another big effect, another e to the plus s size effect. Okay? But when this happens, there might be order 1 violations of our notions of locality. Okay? Now, there's one situation where we know this happens for sure, and that's what I'll talk about in the last half hour here. In the context of black hole formation and evaporation, there is an e to the s here. And as we'll see, the e to the s is because in order to verify you actually lost information. Remember, from what we talked about, so what happens when you form a black hole and it evaporates is that there's a bunch of Hawking quanta that come out. The number of Hawking quanta that come out is around s. Okay? So there's an e to the s dimensional Hilbert space in which those quanta live. And from what we talked about the lump of coal before, in order to see whether or not a state is pure or mixed, you have to make measurements on the almost the entire Hilbert space. Otherwise, even if the state is pure or not, it'll look mixed. You only run into the information paradox when you make order e to the s measurements. And that's where the competing e to the s comes from. I'll say that much more clearly in a second. In the context of inflation and eternal inflation and the picture of the landscape, there's also a natural place where the e to the s can possibly come in. The universe is getting bigger and bigger and bigger and bigger. There's enormous volumes all over the place. Okay? So there's another, at least potentially large number that could offset the intrinsically tiny violations of locality that are there. So I now want to talk about how this works for black holes, and if I have 3 minutes, I'll tell you something about how it works for, how I think it works for de Sitter space. Okay. So let's talk about the information paradox. So here, we actually want to talk about physically forming a black hole and then watching it Hawking evaporate. Okay? So to physically form a black hole, let me remove this part of the geometry. There's some infalling shell of matter that makes the singularity. So this is time and space again. And what's going on is simply the following. We have a time-dependent Hamiltonian, right? We have this matter is falling in, everything is time-dependent. You make a black hole. In this time-dependent Hamiltonian, there's particle production. And that's what the Hawking radiation is. The Hawking radiation is particle production in this time-dependent Hamiltonian. This way we talked about it earlier today for the eternal black hole is a much faster to get the answer for what the temperature is and so on. But I want to stress that the state that we're talking about there is a very different state than the state that you actually make when you make a black hole like this. Now, in order to actually, in order to convince you that I can talk about black hole formation and evaporation without needing to know what's going on at the singularity, and to say what I just said a little more sharply, I should show that I can foliate this space-time with a bunch of space-like surfaces in such a way that there's a nice Hamiltonian that involves me from one surface to another, where the energies are everywhere low, nothing funny is going on. Okay? And there is a set of such spatial slices, the so-called nice slices. So what do they look like? Well, the nice slices at early, so what you want is some spatial slice that contains everything you want at very early times, but also at very late times contains things inside the black hole, and also most of the Hawking radiation that's coming out at very late times. Okay? So, I should have said a few very basic things. In any number of dimensions, you can work this out. In any number of dimensions, so we have some entropy of the black hole, which is the area in units of the Newton constant. The evaporation time for the black hole is always r, the Schwarzschild radius, times s. Okay? In any number of dimensions. And the Hawking temperature is always of order 1 over r. The entropy is mr, always. So the number of Hawking quanta that are emitted is always of order s. Okay? Now, this is very nice because we can take a limit. We can take a limit where I keep the black hole geometry fixed and I send g to 0. Okay? In this limit, the black hole is constantly Hawking evaporating, but it never evaporates. Roughly speaking, because the mass has gone to infinity in this limit. Okay? The evaporation time goes to infinity. The number of Hawking quanta is infinite. And in this limit, as we'll see, there really is an inside and the outside of a black hole, and the information that you throw in is inside the black hole. That's it. There's nothing funny going on, and information is lost in the sense that it's there inside the black hole, but it's okay because the black hole doesn't evaporate. Okay? So from everything that I told you, in any limit where you hold the geometry fixed and you send g to 0, there should be no funny business. There's no room for gravity to screw anything up. Locality is fine. Everything is fine. Okay? In particular, it's not the mere existence of a horizon that tells you all of a sudden that the rules are different. Okay? It's dynamical gravity that tells you the rules are different. It's s not equal to infinity that tells you that something novel is going to happen. But anyway, let's see. Yeah.
Can you repeat this a little bit? I'm not sure I understood. I think it's very important.
Yes. So I'm just telling you facts about black holes that you can trivially work out for yourself. Okay. But for example, the evaporation time in units of the Schwarzschild units is s. The number of Hawking quanta that come out is s. So if we keep the geometry fixed and we send g Newton to 0, s goes to infinity. Okay? So this is a limit where, from what I told you before, you should not expect there to be anything funny with locality. There's no dynamical gravity. Okay? So in this limit, what you see from the geometry is what you get. Okay? And there's no reason to be suspicious. We're going to become suspicious now. Okay? But there's no reason to be suspicious. And it's also fine, because you see the black hole never evaporates. So you throw something in, it's in the black hole. Yes, the information is gone. The information is in the black hole. Okay? But I want to. This is a useful way of thinking because you know, it's not the mere kinematic presence or absence of horizons which changes the rules. It's gravity that changes the rules. Okay? And that's something I think important to keep track of. All right, so let me tell you what these nice slices look like. Let me first tell you what unnice slices are. So here are some dumb slices. Well, one set of dumb slices are just Schwarzschild time. Okay, constant Schwarzschild time. Constant Schwarzschild time is dumb. Why? Because you see, constant Schwarzschild time has the property that that things are becoming infinitely blue shifted. That the Hawking quanta that you see at infinity are incredibly blue shifted near the horizon. And why is that? Well, it's clear from this picture, because I have a bunch of spatial slices, and I'm coming here, you know, and it's getting more and more singular close to the origin. Okay? So we want smoother slices. So those are, of course, the slices that the Hawking used in his computation, and it's okay because the answer is universal. But you know, to really justify that you don't need to know about Planckian physics, we just want to show that it's possible to do it another way. And it is possible. This is what you do. Let me actually extend this geometry a little bit just so I can draw it better. Okay? Take some nice smooth surface that asymptotes to 0 Schwarzschild time. So here's a nice smooth surface that asymptotes to 0 Schwarzschild time. Okay? Call that the P nice slice equals 0 spatial slice. Okay? And now just define all the other spatial slices by the Lorentz boost of that one. That's the isometry of the background. Okay? So earlier nice slices look like that, and later nice slices look like this. So you see, they don't go all the way up to the singularity. Okay? They stay, you know, at a finite region away from the singularity here. But on the other hand, they allow you to cover and go way, way out to very, very late times when, let's say, 90% of the Hawking quanta have come out already. Okay? So here's a set of spatial slices. If I draw it on the Penrose diagram, I hope Raphael drew pictures like this for you. Did he? Good. Okay. So in the Penrose diagram, an early nice slice looks something like this. You know, just normal spatial slices here. And late nice slices look like this. Okay. They stay inside the black hole. And so they include most of the infalling matter and most of the outgoing Hawking quanta. Let's say after the black hole, 90% of its mass is gone, are contained on this nice slice. Okay? So this is a smooth surface. By boosting, I'm constructing all the other ones, so all the other ones are smooth, the extrinsic curvatures are small, energies are small, everything is small. Everything is under control. And there is some nice slice Hamiltonian that evolves me from one spatial surface to another. Okay? This nice slice Hamiltonian is, of course, time dependent. And so what's going on is that as we start forming the black hole, I start making, with this time-dependent Hamiltonian, I start making quanta of energy that go out. Those are the Hawking quanta. And other excitations that fall in, and they're entangled with each other. Okay? Yes?
I didn't understand this. If it's a spatial slice, how can it be inside this 45-degree line and then go out?
Oh, no, because it certainly can. Let me just, let me draw one of them. It isn't a straight line. That's the point. So let me just, okay? So this is a spatial slice.
Any given point of slope is this.
Right. This is a spatial slice. And I'm taking something like this and I'm just boosting it. Okay? Is that clear to everyone? Is that? Okay. All right, very good. So that's what Hawking's computation actually then tells you. So I begin with some initial state here. I have a final state which is pure on this entire nice slice, but it contains entanglement between Hawking quanta here and the things that fell in here. That's why it looks thermal. It looks thermal from the outside because there is entanglement between the Hawking quanta and their partners that were made by this time-dependent Hamiltonian. Okay, so that's a prediction of effective field theory. Okay. Low energy, low curvature, everything is fine. So let's, in particular, let's ask a specific question. Let's look at the, let's draw a dividing line somewhere near the horizon. I don't know, let's put it somewhere near the horizon. And let's just look at the part of the Hilbert space outside. So there's some density matrix for the part outside. Of course, it's a density matrix because it's entangled with stuff inside. And what is its entanglement entropy? So the entanglement entropy is a function of time. There's a very simple prediction for from effective field theory. What does this look like? Well, at early times, as the black hole is forming, it's just going up, right? As the first, second, third, fourth Hawking quantum comes out, it's just going up and up and up and up and up. Okay? Now, this, at around the evaporation time, order S halves, let's say, let's call it order S Hawking quanta have come out. So this is the actual entropy of the black hole, and the entanglement entropy is somewhere around there. In fact, if you do the computation, it's a little bigger. Okay? Now you start seeing the black hole is shrinking. Okay, it's shrinking. Great. Even more, so fewer Hawking quanta are coming out now. They're a little hotter. Okay? And they're even more entangled. They're continue to be entangled with stuff that falls in. So the curve that you predict from effective field theory goes up linearly like this, and then it just gets big. Just keeps getting bigger and bigger until at some time, let's say of order twice the evaporation time or something, where finally the black hole becomes Planckian, then I don't know what's going on anymore here. I don't know what happens at the end. But that's a nice prediction of effective field theory for the entanglement entropy. Okay? Now that's what you get literally from Hawking's calculation. And you see it's not at all what the entanglement entropy as a function of time looks like for a lump of coal. What would it look like for a lump of coal? Well, for a lump of coal, if I draw it over here, from what we concluded last time, the entanglement entropy would also go up, But then it eventually comes back down, and you see that it's a pure state. Okay? Now, actually, how can we be sure that it isn't that in this case, too? I mean, Hawking's awfully smart, but, I mean, he needed the calculation in some semi-classical limit. Maybe there's phases that he's missing. Maybe, couldn't he have screwed up the calculation somehow? Isn't it possible that actually, if you look at this, really, if you did the calculation really properly in effective field theory, you would get something that looks like that? This is great. We can actually completely rule out this possibility without doing any calculations. Okay? You see, in order for it to be true at some late times that it's a pure state again, it would have to be true that at some late time here, let me erase most of these nice slices. It would have to be true that at some late time here, so I start with some initial state. It would have to be true that at this late time, that if I'm looking at the region outside, that the final state here, psi final, was a direct product of some psi out tensor psi in. Okay? That would have to be the answer. That would have to be the answer in order for this to be a pure state outside, in order for it to look like the lump of coal. Okay? And that's just impossible. That's impossible for a very simple reason, again to do with locality. I don't know, let me, wherever I want to put this. You see, if this is true, then let's say that I start with some, let's say I start with some initial state. Let's say there's some initial state here, A. It would have to be the state A evolves to a state in the out-Hilbert space A, tensored with a state in the in-Hilbert space A. If I took the state B outside, it would have to evolve to the same thing, psi out A, tensor psi in, oh sorry, B, tensor psi in B. Okay. But then by linearity, if I take 1 over root 2a plus b, 1 over root 2a plus b cannot evolve, would evolve into 1 over root 2 psi out a psi in a plus 1 over root 2 psi out b psi in b. That's not of the form of a tensor product. Something out, something in. Unless, for some reason, the states psi in B and psi in A were the same for all A and B. Okay? So unless psi in A equals psi in B, for example. Okay? But that's ludicrous. By locality, that's just impossible. Let's say the state A here, you see, because what's going on here inside is something totally innocuous, somewhere in the neighborhood of the horizon, right? Nothing, no funny curvatures, everything is totally fine. If there's an elephant in the state A, there'll be an elephant falling in. If there's a book, there'll be a book. There's no way by locality that the state psi in can be independent of what the initial state is here. So this is called the quantum no-Xerox principle. And it tells you that even independent of any details, it is impossible for the picture of the entanglement entropy for the black hole to look the same as what it does for a lump of coal. By locality. That's what's different about a black hole than a lump of coal. There is a region, causally disconnected region in the black hole, and the information can't get out. Okay? So this is all within effective field theory. And so so this is why Hawking was incredibly sensible in saying that this is what had to happen. Okay. So, and I want to stress, even before we talk about what happens near the end, there's this picture the entanglement entropy just keeps going up and up. This is a prediction of effective field. Okay. Okay, this is also the wrong answer. By the way, it should also be obvious that it's impossible for all the information to come out right at the very end. The black hole has very little mass. Let's say it evaporates in a burst emitting 20 photons. Well, tough luck. There isn't enough room in the Hilbert space of those 20 photons to make up for the amount of entropy which is left. Okay, so that's why, you know, the only reasonable conclusion. So either the black hole just evaporates completely, it's gone, and you just evolve from a pure state to a mixed state. That was Hawking's conclusion. Or maybe the black hole settles down to a remnant that contains enough degrees of freedom. So there's some Planckian object that sits there with a bajillion dimensional Hilbert space inside it to continue to explain the entanglement. That's kind of crazy. Or something which is very similar. There's a remnant that spends a really, really, really long time to decay to evade this problem we just said that 20 photons aren't enough. And anyway, that has basically the same problems as an infinitely long-lived remnant. Okay? So that was the conundrum. But evolving from pure states to mixed states is also not something that really makes sense. So the right answer, by the way, the right answer for the entanglement, so I want to stress, here we don't know what's going on. I want to stress this is an experimental observable. Okay? How would you actually measure this? Of course, it's quantum mechanics, so you have to repeat the experiment over and over again. You have to set up exactly the same conditions for forming the black hole over and over again. Okay? But you do the experiment a huge number of times. You measure everything you can about the outgoing radiation. You construct a big density matrix. You measure all the components of the big density matrix. And you can do it. It's observable. And you can form this entanglement entropy. There's a prediction from effective field theory. And you can just check. It's an experimental question if it's right or wrong. Okay, well, we haven't done the experiment, but we believe that the answer is that that's not right. And instead, what it looks like is this. The entanglement entropy looks very similar here. But then it is like a lump of coal. And it does go back down to 0. And in fact, the entanglement entropy here is always bounded by, and in fact hugs the curve of the area of the black hole divided by 4g. In other words, the entropy of the black hole at every moment of its evaporation. Okay? So we think this is the right answer. But if that's the right answer, you see there's an order 1, even before talking about Planckian physics, there's an order 1 disagreement between long-distance effective field theory and the right answer. Okay? So why is this happening? First of all, by the way, so what this picture is supposed to say is that at early times, the difference between the right answer and the effective field theory answer is e to the minus s, minuscule. That makes sense from our lump of coal analog, right? It should be only when you see, remember, in the lump of coal, until you got to k of order n, the effect was e to the minus n minus k. So basically e to the minus n. Okay? So until you measure s-half Hawking quanta, or e to the s-half different states associated with the s-half Hawking quanta, you're not going to see anything. The effect is going to be exponentially tiny. Only after finally being able to measure all e to the s quanta should you start seeing a difference. And then you see a difference which is order 1. Okay? But how come? Why is it that that effective field theory can be breaking down so badly? Well, this is a case where it is an e to the minus s effect that's being enhanced by an e to the s. And the e to the s here is that you're asking an incredibly exclusive question. See, in order to be able to confirm this prediction of the effective field theory, in order to be able to tell the difference between the effective field theory and the right answer, we just said that I have to be able to measure at least an e to the s halves dimensional part of the Hilbert space. Okay? In other words, if I measure some fixed number, an e to the 100 by e to the 100 part of the Hilbert space, the difference between the right answer and the effective field theory answer would be e to the minus s, in that tiny. Okay? In order to see the difference to begin with, I have to work really hard to construct an e to the s by e to the s matrix for rho. Okay? I have to make e to the s separate measurements to make a gigantic density matrix. And so that's the e to the s that has a chance of offsetting the intrinsic e to the minus s fuzziness in our notions of locality. Let me say this another way. If we were to compute few-point functions, okay, the few-point functions that the effective field theory calculates is the same as the right answer, plus tiny corrections, e to the minus s minus k. It's only for s-point functions that the effective field theory gets the answer wrong by order 1. Okay? So again, this is a perfectly decent limit as you send g to 0. If you send g to 0 holding the geometry fixed, the question that the effective field theory is getting wrong is a stranger and stranger question. Okay? It's getting it wrong for an s-point function, not for a few-point function. Okay. And so let me say this another way. The right answer tells you that the density matrix is pure. Effective field theory tells you that the density matrix is maximally mixed. Okay, so these density, they look very different. But they're not very different than enormous dimensional Hilbert space. Okay? After all, if I take the matrix e to the minus s and I sprinkle e to the minus s's along everywhere else, then on another basis, that's the same as 1, 0, 0, 0. Or said another way, these things look different for the one state that's 1. But for all the other states, the 0 and the e to the minus s aren't that different from each other. Okay? So it's again a statement. So the invariant statement is that you're screwing things up when order e to the s, when you make measurements on order e to the s states. Okay. So from here, I think we can take away. Yeah, yes. Sorry? Right. Exactly. Well, right. So that's right. So this says that the notion of local evolution is wrong. Okay? Now, we have no reason to expect it to be exactly correct. Okay? We just went through these arguments saying locality is an approximate notion in gravity. Okay? But it seemed like it's just such a tiny, tiny correction that how can it possibly be important in this macroscopic question? Okay? And what I'm saying is that, so local evolution is wrong. So let me just say this because I'm just giving you the right answer here. Okay? So that means that the states inside here are not in an orthogonal part of the Hilbert space to states here. Operators here do not commute with operators here. Okay? Despite the fact that that's all apparently guaranteed by local evolution, there is something wrong. There is something that's the wrong answer. Okay? The way that wrongness shows up is what I'm trying to say is that I'm trying to make less surprising or try to make it more plausible why that happens here, because you only notice it when you make an incredibly specific, when you ask an incredibly exclusive question involving e to the s states. Okay? But indeed, locality is wrong, even macroscopically wrong. And I should say that Maldacena and then Hawking, in the context of the ADS-CFT, set up this question in ADS for ADS black holes, and what they indeed saw and could compute was the difference between the naive effective field theory answer and the right answer for two-point functions. And indeed, there is a difference that the CFT tells you is there that you don't see in the bulk theory of order e to the minus s in the two-point function, which you can interpret as another saddle point, another configuration, instead of having the ADS black hole there, having a gas of gravitons there, contributing to that quantity. And that's extremely nice to start seeing explicitly the difference between the right answer and the naive gravitational answer. But this fact that the correction looks like another approximate semi-classical geometry is something that does not obviously extend to the case where the differences start becoming really big. Okay? So the fact that there are tiny e to the minus s differences in the two-point function is not something that would surprise you, period. What's surprising is that in a macroscopic s-point function, it's order 1 different. And we still don't understand that. Okay? So that's something we don't have quantitative good control of. But I'm telling you the right answer. Okay? So the right answer ultimately is that the picture of the state on the spatial slice, with the part inside and the part outside independent, is wrong. Okay? Now we can ask, when does effective field theory? So now maybe we can now. I don't know the full correct theory yet, but I want to come up with a better characterization of when effective field theory is breaking down. So it is not when s is of order 1, so that things are of order the Planck scale. So the new proposal is that effective field theory breaks down when it forces you to consider states which have entanglement entropies that exceed the entropy of the relevant horizon. Okay. So let me say this another way. So let me say this. When we get size with s bigger than, or s starts becoming comparable to the area of some horizon over G. Okay, so there's this rough idea. There's a rough idea of holography for black holes. That's not as well defined as holography in ADS-CFT. But the rough idea is that a black hole doesn't have more than e to the Hilbert space for everything inside of black holes can't be bigger than e to the s dimensional. Okay, s is the area in units of G. By the way, this is an exercise that you should do. Often people say that this means that effective field theory must be vastly overcounting degrees of freedom. And this is just silly. It's true that effective field theory without gravity would tell you that there's an infinite number of degrees of freedom in a certain volume. But if you're not a completely stupid effective field theorist, and you count all the states you're allowed to have in a given volume, well, you would notice something, right? Well, there's one vacuum state. Great. You might put a cutoff near the Planck scale, and then you count how many one-particle states are there. Well, it's the volume of the region in Planck units. How many two-particle states? Well, it's that answer squared over 2 factorial. Okay? And you would maybe naively keep going and add all of those up to get e to the volume in Planck units. But you would notice something, that as soon as you got to like a million particle state, hey, these particles have so much energy they would be collapsing my region into a black hole. So maybe I don't know how to count them anymore. I can't say that just the tensor product of all these free states is another state. And if you just count the states that you know for a fact aren't black holes, not only don't you get e to the volume, you don't even get e to the area. You get e to the area to the 3/4 in 4 dimensions. Okay? Way less than the entropy, way less than the holographic bound. Okay? In fact, you know this because you know that the object with the most entropy in a given region is the black hole. If you take a ball of gas and it's about to collapse into a black hole, its entropy right at the moment where it collapses into a black hole is the area to the 3/4, not the area. There's more degrees of freedom in gravity, not less. Okay? There's more degrees of freedom than the ones that you can naively count in effective field theory. But what's happening here is that, maybe I don't know how to talk about this. Maybe I don't know how to talk about a finite dimensional Hilbert space inside. But the Hilbert space outside is certainly infinite dimensional. And I can do as many measurements as I want outside. I can do whatever the heck I want to do outside. But the nice slice evolution is making a state for me where the entanglement entropy that I can measure outside exceeds the entropy of the black hole. Because the entanglement entropy is equal for both parts of the subsystem, that tells me that the number of states inside must be at least e to the s. And it's when that happens that effective field theory starts getting the wrong answer. So effective field theory is wrong, not when curvatures are large, and not that's part of it. But it's really when it forces the existence and requires the existence of more than e to the s states inside a given volume. Okay, that's right. More than the e to the s states associated with the region behind a horizon of area A, where S is A over G. Okay. Okay. So that appears to be the lesson that we can draw here. Effective field theory breaks down when it doesn't not allow you to talk about too many states excited at the same time. Okay? You're not allowed to have, and it breaks down when it forces you to invoke more than e to the s states. Okay. So this tells us then to be wary. So I have no time to talk about de Sitter space, unfortunately. But you can read my last paper, second last paper. But it tells you then to be wary, okay? That even at low curvature, even at low curvatures, it's possible that you're getting misled by a semi-classical picture of the spacetime. Here we got totally misled by the local picture of the spacetime, and it's possible that we could be getting misled by the semi-classical picture of the spacetime in eternal inflation as well. What's a little confusing about the de Sitter case is for black holes, it's kind of obvious what we should be talking about by what we should mean by the entropy of the object. There's a black hole, something that's sitting there. It has a finite volume. Whether the number of degrees of freedom is volume or area or something, it's sort of obvious that it's finite. Okay? Whereas de Sitter space, which also has a finite entropy, does not obviously have, it looks infinite. Everything is infinite. So in what sense does it have a finite number of degrees of freedom? In what sense are we supposed to think operationally about what that entropy is? And well, one thing you can do, which we did in this paper, and I won't say much more about it, is regulate the question by imagining it as being part of inflation. So if you're inflating for a long time and then inflation ends and you see all these modes coming back into the horizon, all the modes coming back into the horizon came to you from the inflating past, so you can associate them all with a state in de Sitter space. And counting the number of modes that you get is an operational meaning to the number of states there were in the de Sitter space. So if there's some meaning to de Sitter entropy, there should be some limit to the number of these modes that you can see. And actually, interestingly, there is. In theories that inflate, where inflation ends and eventually all the modes come back in and the perturbations are small so you can reliably count everything, it turns out that the number of e-foldings of inflation is always limited by s. So you never see more than e to the s modes. You never beat the cosmic variance limit on any quantity that you can associate with de Sitter space by more than e to the minus s. Okay, so there is some meaning, some operational meaning to this finiteness of the entropy. But it also suggests that no more than e to the s space-time Hubble volumes of de Sitter space make sense. And that more than that many Hubble volumes, space-time Hubble volumes of de Sitter space, should have the same relation to one given set of them as the outside and the inside have here. Okay? So roughly speaking, I think there's very likely some sense in which regions very, very far away on the spatial surface in one of these pictures of eternal inflation are actually scrambled versions of things inside a sufficiently large patch, in much the same way as the things falling inside the black hole are encoded in some scrambled way outside. In fact, this is the last thing I'll say, there's, I think, a very good analogy with trying to understand the dynamics of people who fall into the black hole and the landscape. Okay? You see, people who fall into the black hole, they see different laws of physics than the people outside. Okay? They see some time-dependent Hamiltonian. They see different things, especially as they approach the singularity. There's all kinds of non-uniqueness in what they see. You might complain, well, they all see the same microscopic laws of physics, which is true. That's also true in the landscape. When you compactify, everyone eventually sees the same microscopic laws of physics. But in detail, they see different things. Okay? Furthermore, all of these things are approximate. You know, these guys, there are no perfectly sharp observables associated with them because they don't live forever, because they hit a singularity, they can't do experiments over and over again, etc. Okay? These guys outside can, but these guys can't. Similarly, in cosmology, we see a variety of different laws of nature. Of course, again, it just looks like time-dependent Hamiltonians. Because it's metastable, the time dependence is kind of very bumpy. So it looks like one set of things for a long time, then you transition to another set and transition to another set. But that I think is probably a detail. This looks a little smoother. But in both cases, we just see some history with some effective Hamiltonian governing what we see locally. Also, in the landscape, we don't have perfectly sharp observables associated with us because we're in this de Sitter space. We can't make arbitrarily sharp measurements and so on. Okay. Here, you might want to ask the question then, well, what are the chances that I'm this guy? Or what are the chances that I'm that guy or that guy? Okay. In fact, you see the picture inside is not that different, terribly different from de Sitter space. In the sense that these guys, their future light cones don't overlap. But what this picture of complementarity suggests is that, in fact, this guy and a sufficiently far away guy, even inside, never mind also outside, are, well, these operators don't commute. That means that very likely, sufficiently far out here, even inside, the experience of this guy and that guy are just scrambled versions of each other. Different parts of exactly the same Hilbert space. And that they all are embedded inside some infinite dimensional Hilbert space in a sharper way that the outside observer can talk about. But I think that already complementarity suggests here that something way far out, that way, in the picture of eternal inflation might just end up being a copy in very scrambled variables of what we see inside our own approximate cosmological history. Anyway, that's all very, very vague, but I really think it's very unlikely that we're going to make progress on the very big question of the landscape until we understand this comparatively easier question of how to understand in more detail what happens to the infalling observer. And trying to put some mathematics to these words about complementarity, even in toy models, I think will help us make some progress. All right, so this is a question that I suspect someone will figure out the answer to, and everyone will say, "Duh." But it involves some great idea, and I hope you guys find it. Thanks.